Thank you for being here. We are starting our live stream about rock planets, space wonders. Are you ready? If you're ready, I am ready too. Let's start.
Today we are undertaking a truly radical thought experiment. One that kind of turns the whole concept of the habitable zone completely inside out.
We are indeed. We're turning off the stars, so to speak.
Right, we're going completely dark.
Yeah.
Figuratively and literally.
We're diving into the complex, really strange world of rogue planets. These are worlds that have been, well, violently ejected from their parent star systems, or maybe never even latched onto one in the first place.
And now they just wander the vast, frigid interstellar void between the stars, sometimes even between galaxies.
Exactly. And the fascinating thing is, this isn't just theoretical anymore. Not like it used to be.
Okay, let's unpack this a bit then. The source material you shared, it gives us this really comprehensive physics-based framework. Not just to count these worlds, but to seriously calculate their potential for life.
And even complex intelligence, potentially. Surviving on them.
Right. So our mission today is to understand the specific, non-stellar mechanisms, the ways life could possibly sustain itself in perpetual darkness. It feels like it almost redefines the basics of astrobiology.
It really does. And what's just staggering here is the sheer scale involved, which fundamentally changes the whole conversation.
So?
Well, historically, we thought rogue planets were, maybe cosmic oddities. Rare. But recent surveys, using gravitational microlensing mostly.
The technique where the planet's gravity briefly magnifies a background star.
Precisely. Those surveys strongly suggest these free-floating planets are incredibly numerous. The current thinking, under several quite plausible models, suggests they could actually outnumber the planet's safely orbiting stars.
Outnumber them? Seriously?
Potentially, maybe 1-to-1, maybe even more. And that fact alone, it completely alters the math. It forces us to ask where the majority of life in the Milky Way might actually reside. Maybe it's not around stars like ours.
Wow. Okay. That definitely sets the stage. So here's where it gets really interesting, I think. When we talk about a rogue planet, it's not just one thing, is it? Not some single category of frozen rock.
Not at all. The sources break them down into 5 pretty distinct classifications, and each one has its own unique origin story, its own chemistry.
And its own, frankly, bizarre potential for hosting life.
Exactly.
Yeah.
We need to classify them because the physics of how life might survive, or even start, changes completely depending on which type you're looking at.
The mechanism is everything. Makes sense.
Yeah, you have to consider things like, did it keep an atmosphere after being ejected? Does it generate its own heat internally? Does it have a magnetic field to shield it?
And all those factors depend on how it got there in the first place. Its origin story. Hashtag tag car A. Type I, stellar orphans. The ejected Earths. Okay, let's start with Type I. These are the stellar orphans. These are maybe the easiest ones to picture in your head.
I think so. They're essentially planets could be rocky like Earth, could be icy, maybe even small gas giants that formed normally in a star system.
But then got violently kicked out.
Right. Usually during the chaotic early days of a planetary system, when gravitational interactions are really strong and unstable, planets get scattered, some get thrown out entirely.
So they're basically exoplanets that lost their anchor star. Compositionally familiar, like you said, a sort of misplaced Earth or Mars.
Potentially, yes. Now, the key to their habitability, according to the models we're looking at, hinges on 2 critical factors. First, they hold on to some residual heat from their formation.
Leftover warmth from when they first coalesced.
Exactly, and from the violence of the ejection itself, potentially. This heat diminishes over time, of course, but it can persist for billions of years deep inside.
Okay, that's one factor. What's the second?
The second, and this is absolutely crucial, is that they must have, or must somehow retain, a thick, dense atmosphere. Ideally, one rich in molecular hydrogen.
Hydrogen. Why hydrogen specifically? Not like carbon dioxide or water vapor?
Hydrogen is an incredibly powerful greenhouse gas. Far, far more effective than CO2 or water vapor, especially at the low temperatures we're talking about. It acts like a super efficient thermal blanket.
So it traps that internal heat.
It insulates the planet brilliantly, trapping both the residual formation heat and any ongoing internal heat generation, preventing it from just radiating away instantly into the cold of space.
Without that thick hydrogen shell.
The surface, and probably much of the interior, would freeze solid almost immediately, right down to the core, practically. Any water would be permanent ice.
So that insulation really is the difference between just a dead ice ball and a world that might still have liquid water and maybe life.
It's the make or break factor for type I habitability. This leads to the cold Earth's hypothesis, which really centers on these kinds of worlds.
And the life potential here, it's focused on subsurface oceans, right? Hidden beneath maybe kilometers of ice like we think might exist on Europa or Enceladus in our own solar system.
That's the leading idea. The energy source for such life has to be persistent, obviously, since there's no sunlight. It primarily comes from two places.
Okay, what are they?
One is radiogenic decay. The slow breakdown of long-lived radioactive elements, think uranium, thorium, potassium, deep within the planet's mantle and core.
Like Earth's internal radioactivity.
Exactly the same process. It continuously releases small but steady amounts of heat over billions of years.
On the second source.
The other key source, especially if the planet was lucky enough to keep hold of any large moons during the ejection,
The moon.
is tidal friction. The constant gravitational push and pull between the planet and its moon, or moons, flexes the planet's interior. That generates immense reliable heat.
Like Jupiter heating its moon Io through tidal forces.
Precisely. So type I worlds, if they're habitable, rely entirely on this internal geothermal heat, the radiogenic decay, and maybe chemical energy gradients near hydrothermal vents, mimicking the deep sea ecosystems on Earth, but potentially on a much grander planet-wide scale beneath the ice. Hashtag B, Type 2 primordial wanderers, the gas giants.
All right, moving on to type 2. The primordial wanderers. Now, these sound fundamentally different. They never had a star to begin with.
Correct. They're a whole different beast. They didn't get ejected. They formed directly from the collapse of a giant molecular cloud, the same way stars do.
But they didn't ignite.
They just didn't accumulate enough mass. They fall below the minimum threshold for nuclear fusion to start in their core. That's roughly less than 13 times the mass of Jupiter.
So they're essentially failed stars. Or maybe super Jupiters.
Failed stars is a good way to think of them. Massive gas giants, mostly hydrogen and helium, like Jupiter or Saturn. But because they formed through direct gravitational collapse, not accretion in a disk, they have immense internal pressure and significant internal heat left over from that formation.
They sound more like brown dwarfs, those objects between planets and stars.
Very much so. They likely have complex, dynamic atmospheres, powerful weather systems, maybe even enormous lightning storms and aurora driven by their internal heat and rotation.
The environment sounds incredibly harsh, though. Extreme pressures, high winds, probably weird chemistry.
It absolutely is. But that immense pressure is actually key. As you descend deeper into the atmosphere, the pressure and temperature rise dramatically. The model suggests there could be deep, warm layers where conditions might allow for, well, some kind of exotic chemistry.
But life. Where would life
Yeah.
exist? There's no solid surface, no ocean floor like in type I.
Right, this is where it gets really speculative. We have to abandon the idea of surface life entirely. We're talking about hypothetical aerosol life.
Organisms just floating
Yeah.
in the clouds.
Essentially, yes. Similar to the kinds of life Carl Sagan and others speculated might exist high in Jupiter's atmosphere, buoyed up in temperate layers.
But what would power them? What's the energy source way up there? They don't have that geothermal core right beneath them.
That's the crucial question. The novel hypothesis here is what the sources call floating biospheres that might be sustained entirely by the planet's massive electrical storms.
Lightning. Life powered by lightning.
Potentially. We know these huge gas giants can generate colossal electrical potential differences in their atmospheres, leading to incredibly powerful, frequent lightning. Life could, in theory, evolve to tap into these vast charge gradients and particle flows as an energy source.
Like a form of electrical metabolism.
Something like that. Instead of breaking down chemical bonds for energy, like life on Earth, they might directly exploit the persistent electrical differential between atmospheric layers, using that energy flow to maintain themselves, repair damage, replicate, using the raw chemical materials available in the clouds. It's wild stuff.
Yeah.
Hashtag C. Type 3 cryogenic giants, the ice worlds.
Okay, type 3. Cryogenic giants. These sound like ejected ice giants, maybe. Like Uranus or Neptune, but cast adrift.
That's the idea. Ejected ice giants, or perhaps super Neptunes, even larger, they'd consist mainly of water, methane, and ammonia ices, likely with incredibly thick frozen outer shells.
So similar to type I in having a solid exterior, but much larger and icier.
Right, but the internal conditions are predicted to be quite different due to the sheer scale and pressure. These worlds could potentially host deep ocean environments, but under truly alien conditions.
How so?
Because of the immense pressure exerted by maybe hundreds or thousands of kilometers of overlying ice, The water beneath wouldn't be like Earth's oceans. It would be compressed into exotic high-pressure phases of ice, like ice 6, ice 7.
Different crystal structures for ice.
Exactly. Stuff that only exists under incredible pressure. But crucially, beneath these exotic ice layers, the models suggest these interiors might still host vast, warm, high-pressure ionic oceans.
Ionic oceans, what makes them ionic?
At those extreme pressures and moderate temperatures, a significant fraction of the water molecules themselves can be forced to dissociate into ions H plus and OH, or maybe H3O plus and OH. So you don't just have neutral liquid water, you have a highly electrically conductive fluid, an ocean of charged particles.
Wow. And these interiors would be active.
Likely very dynamic. Deep convective layers within these ionic oceans could generate strong, long-lasting magnetic fields. And that magnetic shield would be absolutely vital.
For radiation protection.
Yes, to shield any potential deep-sea life from the constant bombardment of high-energy interstellar cosmic rays. Without a magnetosphere, that deep ocean might be sterile, despite the heat and water.
So the life potential here sounds like it's back to chemosynthesis, like deep-sea vents on Earth feeding on chemical gradients.
That's the baseline hypothesis, yes. Similar to Earth's hydrothermal vent ecosystems thriving in total darkness on chemical energy. But there's also a newer, more specific idea floated for these worlds.
Oh, what's that?
It's called subcrustal metabolism. This proposes that life forms might actually exploit the electrical charge differentials that naturally arise at the boundaries between different phases of matter down there.
Like the boundary between solid ice and the liquid ocean.
Exactly. Or even between different phases of high-pressure ice, like the boundary between ice 6 and ice 7, or between ice and the liquid ionic water. These phase boundaries can apparently set up powerful electrochemical gradients.
Like a natural battery.
Essentially, yes, a sort of geological battery formed by the physics of high-pressure phase transitions. Life could potentially tap directly into that electrical potential for energy, life powered by phase change physics itself. It's another really out there but physically plausible idea. #hashtag D. Type 5e carbon worlds. Alternative chemistry.
Okay, Type 5e takes us even further out. Carbon worlds. These sound like the most alien concept yet. They require, what, a totally different starting chemistry?
They really do. They push the boundaries of imagination. The idea is that these planets might form in environments that are unusually rich in carbon compared to oxygen, maybe around specific types of carbon-rich stars, or from peculiar fragments of molecular clouds that have a high carbon to oxygen ratio.
And what would that mean for the planet itself?
Instead of silicate rocks and water ice dominating the geology, you'd have a world where carbon compounds are the main building blocks. Imagine surfaces potentially covered in crusts of diamond or layers of graphite, maybe graphite dunes instead of sand dunes.
Diamond crusts. Seriously.
Under the right temperature and pressure conditions, yes, it's theoretically possible. The environment would likely be very dark, absorbing heat efficiently. And if there are liquids, oceans, they wouldn't be water.
What would they be?
They'd likely be composed of hydrocarbons, things like liquid methane, ethane, maybe even thicker acetylene tars acting as the solvent for life instead of water.
So this is the realm of truly alternative biochemistry.
Absolutely. Forget water-based life. Here, we're forced to consider biochemistry based perhaps on silicon chains instead of carbon, or using those liquid hydrocarbons as the medium for life's chemical reactions.
And the sources push a specific wild idea here too, don't they?
They do. It's dubbed diamond cell life. And it is truly mind-bending.
Good on.
The hypothesis is that organisms could potentially utilize the incredibly stable, predictable, repeating lattice structure of diamond, or maybe complex graphite forms as well, as both their physical structure and potentially even a framework for computation or information storage.
So that they wouldn't be like squishy biological cells as we know them.
Not at all. They might be semi-crystalline entities, using slow hydrocarbon reactions perhaps, occurring at the crystal interfaces to grow, repair, or maintain their structure over vast timescales.
So the organism is the mineral lattice, in a way,
No.
or integrated into it.
That's the provocative idea. It forces us to completely abandon our water-centric, soft matter bias about what life is. Imagine life that doesn't rely on the fluid dynamics of liquid water for its internal processes, but is fundamentally integrated into the crystalline geology of the planet itself.
A truly geological life form.
Slow, incredibly durable, potentially capable of surviving in that stark, high-pressure, carbon-saturated darkness for maybe billions of years. It's about as alien as you can imagine. #E type E, artificial or engineered rogues. the speculative edge.
Okay, that brings us to the final category, type V. And this one is explicitly labeled the speculative edge.
And for good reason, we're now talking about artificial or engineered rogues. These aren't natural planets at all, necessarily.
They're constructs, built or modified by civilizations.
That's the hypothesis. Massive structures, potentially planet-sized, constructed, or perhaps profoundly modified, like hollowing out a natural rogue by extremely advanced civilizations.
For what purpose? Interstellar arcs.
Data storage. All of the above are possibilities. Maybe long-term data repositories, maybe generation ships carrying populations between stars, maybe mobile energy collectors harvesting interstellar gas or dark matter. Who knows?
The ultimate stealth ship, really. Using an entire planet or something that looks like one as camouflage.
It would be effective camouflage, certainly. The composition would be engineered composite materials, potentially vast, hollowed-out interiors with controlled environments, artificial lighting, meticulously managed internal thermodynamics.
Then internal heat management seems key. If they have, say, fusion reactors or massive computer cores inside.
They have a huge waste heat problem.
Exactly.
They'd need incredibly sophisticated ways to dissipate that heat efficiently, but crucially without broadcasting an obviously artificial thermal signature to the galaxy.
So they try to mimic a natural planet's heat signature.
They'd likely have to modulate their internal energy flows, maybe radiate the heat very diffusely, perhaps mimicking the slow cooling curve of a natural Type I or Type 3 rogue planet to avoid detection.
And the most compelling, or maybe disturbing, speculative idea attached to this type.
That would be the concept of the nomad consciousness.
Which is?
The idea of potentially non-biological, maybe AI or fully post-biological civilizations that have uploaded themselves or exist as pure information or energy patterns.
And they migrate between star systems using these planet-sized vessels.
Precisely. They might view the entire galaxy as their environment, their resource pool, using controlled internal power sources and maybe subtle trajectory adjustments over millennia to navigate the interstellar currents.
They become the ultimate survivors. Having solved the energy problem, bypass the need for a star entirely.
They'd represent a kind of post-biological survival mechanism, deliberately disguised as just another cold, inert world drifting through the darkness. Masters of energy and information, hidden in plain sight. It's the far, far edge of speculation, but grounded in the idea of long-term survival strategy. Okay, so we have this incredible zoo of potential rogue worlds, from ejected Earths to diamond planets to artificial constructs. If we want to connect this diversity back to the bigger picture of life in the galaxy, we really need a more rigorous way to quantify their potential.
Right, we can't just wave our hands and say life might exist. We need numbers, probabilities.
Exactly. Our sources emphasize moving beyond the simple star-centric idea of the habitable zone where liquid water can exist on a surface thanks to a star. That just doesn't apply here.
So we need a new framework.
Which the sources provide. It's built around two key metrics, the life probability coefficient, or LPC, and the intelligence probability coefficient, IPC.
And this framework is crucial because it forces us to really define how life could survive when you take away the main energy source we always think about, starlight. It's a tool for comparing apples and, well, very strange oranges. Hashtag tag tag A. Defining the coefficients.
So the LPC. It's designed as an intrinsic score for any given world, representing the fundamental probability that it could sustain some form of metabolism, likely microbial life, at least initially.
And how is it calculated? It's not just one factor, is it?
No, it's based on a multiplicative model. The formula looks like this: E times C times A times M times M.
E times C times S times I times M. Now, the fact that it's multiplicative, not additive, is really important, isn't it? Explain why that matters so much.
It's absolutely critical. It reflects the harsh reality that life seems to require the simultaneous fulfillment of all these necessary conditions. If any single one of these factors drops to near zero, the whole product collapses.
So you could have perfect chemistry, perfect stability, loads of internal energy. But if there's absolutely no solvent, say,
then LPC is zero. Life, as we can conceive it, is impossible. Or, say the environment is incredibly unstable, Sanders is near zero, due to constant volcanic resurfacing or atmospheric collapse. Even if energy or e-nullers and chemistry are great, life probably can't persist.
And for rogue planets, the big killer is the first term, e-nuller.
Right. The energy availability from stellar irradiance is essentially zero for a rogue planet floating in deep space, which means for a rogue to have any chance of life, a non-zero LPC, the other factors have to be significantly high to compensate, particularly the internal energy and the multiplicity factor.
Okay, let's quickly break down those 5 factors again, specifically thinking about rogues.
Sure. E, energy availability. As we said, stellar energy is negligible for rogues. This is their biggest hurdle compared to star-bound planets.
Got it.
C, chemical richness and solvent availability. This covers the basic building blocks, essential elements like carbon, nitrogen, phosphorus, plus the presence of a liquid solvent, water, hydrocarbons, whatever, and crucially, redox couples.
Redox couples. Those are chemical imbalances that life can exploit for energy, right? Like oxygen and hydrogen reacting.
It's exactly chemical potential energy.
Mm-hmm.
Rogue planets, being cold and potentially preserving volatile ices deep inside, might actually score quite well on towers, especially beneath their surfaces.
Okay, next is S.
S, stability, longevity. This is about how long the potentially habitable environment lasts. It's normalized to a billion-year timescale in the model. And here, rogues might actually have an advantage.
Really?
Because those deep subsurface environments, protected by kilometers of ice or rock, are buffered from external threats like asteroid impacts, solar flares, or nearby supernovae. They could remain stable for incredibly long periods, potentially giving a very high score.
Makes sense. Then I, internal energy.
Internal auxiliary energy sources. This is the absolute lifeline for a rogue world. It's the geothermal heat, the radiogenic decay we talked about, and especially tidal heating if moons are present. We have to stress that while radiogenic decay is weak, it's incredibly persistent, lasting billions of years, so all dollar can be significant and long-lasting for many Type I and Type 3 rogues.
And finally, M.
M, multiplicity system complexity. This factor accounts for the presence of things that add complexity and potential energy sources to the system, mainly moons, but maybe also rings, or even being part of a binary rogue pair. This factor, as we'll see, is often the key difference maker for rogue habitability.
Okay, so that's LPC for basic life. Then you escalate to IPC for intelligence.
Right. The intelligence probability coefficient builds on LPC. It adds extra constraints needed for the evolution of complex, perhaps technological intelligence.
Which requires more than just basic survival.
Much more. The formula is text LPC times K times $10. So you start with the basic life probability, LTC, and multiply it by 2 more factors.
K and T, what are they?
K, complexity factor. This tries to capture the potential for complex life to evolve. It considers things like the variety of environmental niches available, the energy flux density, how much energy is available per unit area volume, and the potential for complex ecosystem interactions.
And subsurface oceans might score lower here. More uniform environments.
Potentially, yes. A deep, dark ocean might be very stable, Subbles is high, but perhaps lack the diverse range of niches. As lower that drive complex evolution on a very planetary surface like Earth's T time factor. This represents the fraction of the required evolutionary time that the habitable conditions actually persist. Life might start relatively quickly, but the evolution of intelligence, based on our one example, seems to take billions of years. If the rogue's internal energy source, say tidal heating from an unstable moon capture, only lasts for 1 billion years, then T dollars will be low, even if LPC was initially high.
So IPC is always going to be less than or equal to LPC.
Always. It reflects the common sense idea that complex intelligence is likely much rarer and harder to achieve than simple microbial life. #BR. The crucial role of moons. Multiplicity factor M.
Okay, let's really unpack this multiplicity one. You said it's a game changer for rogue planets. Why is it so critical?
Because it's the most potent way for a rogue planet to generate a strong, persistent internal energy source that can compensate for the lack of stellar energy. It's the multiplicity multiplier.
And this mainly comes from moons that survive the ejection.
That's a major pathway, yes. Retained moons. When a planet gets violently ejected, any moons that are already orbiting it very closely might remain gravitationally bound and get carried along for the ride.
And their gravity keeps interacting.
Constantly. The mutual gravitational tugging between the planet and its moon, or moons, leads to continuous tidal friction. Both bodies literally get stretched and squeezed by gravity.
Which generates heat. Lots of heat.
Potentially enormous amounts of heat dissipated right in the interiors of both the planet and the moon. This tidal heating mechanism can be far more powerful, more energetic than just the slow radiogenic decay. And crucially, it can persist for billions of years as long as the orbits remain somewhat eccentric or inclined.
So it's not just about having heat, it's about having enough energy flux, enough power to drive geological activity, maybe hydrothermal vents.
Exactly. Life doesn't just need warmth, it needs energy gradients, chemical turnover. Tidal flexing provides that. It keeps subsurface oceans liquid, drives hydrothermal circulation, bringing nutrients up from the rock, and maintains those vital redox couples that life needs.
That makes the dollar factor incredibly powerful in the LPC calculation.
It can boost the dollar score dramatically.
Right.
And there are even more exotic possibilities. Imagine a large rogue planet glowing faintly in the infrared from its own geothermal heat.
Yeah?
It might actually reflect some of that faint heat onto the surfaces of its close orbiting moons, creating a kind of perpetual, incredibly dim twilight in the mid-infrared spectrum.
Dark light. For organisms evolved to see heat.
It's a possibility, a bizarre form of illumination in the deep dark.
But what if a rogue gets ejected and doesn't manage to keep its moons? Is it just out of luck for this dollar factor boost?
Not necessarily. The Nollar factor also accounts for captured companions. Out there in the interstellar void, relative speeds between objects can be quite low. A wandering rogue planet might gravitationally encounter and capture other smaller objects.
Like asteroids, or even another small rogue planet.
Precisely. It could capture asteroids, comets, dwarf planets, or even form a partnership with another rogue, creating a binary nomad system.
And these captured companions would also cause tidal heating.
Yes, if the capture results in a relatively close eccentric orbit, you get dynamic tidal heating, just like with retained moons. Plus, these captured bodies can significantly enrich the system with new chemicals, particularly volatiles like water or ammonia, boosting the chemical richness factor.
Okay, so multiplicity is huge for basic life,
Yeah.
LPC. What about for intelligence, IPC? You mentioned tidal circadian biology. That
Yeah.
sounds fascinating.
Right. For intelligence to evolve, the thinking goes, you need environmental complexity and reliable, predictable rhythms or cycles. These act as stimuli for developing brains, fostering pattern recognition, memory, prediction.
On Earth, that's the day-night cycle, the seasons.
Yeah.
Driven by the sun and our axial tilt.
Exactly. On a rogue planet with moons, you wouldn't have a solar day-night cycle, but you would have other complex, predictable cycles.
Like what?
Cycles of eclipses as moons pass in front of each other or block the faint galactic light. Rhythmic variations in the tidal forces felt within the ocean. Predictable fluctuations in the planet's magnetic field strength as the moons pass through different regions of the magnetosphere.
So life's internal clock, its circadian rhythm, might not be set by light, but by gravity or magnetism.
That's the idea of tidal circadian biology. Organisms, and eventually maybe intelligent life, could evolve biological clocks synchronized to the complex but fundamentally predictable gravitational and magnetic oscillations of their multi-body system.
A clock set by the tides, not the sun.
It's a profound shift in perspective. But that reliable, complex environmental stimulation provided by the moons could be exactly what's needed to provide the long-term cognitive challenges that drive the evolution of complexity and eventually perhaps intelligence, IPC, hashtag Shabasi, comparative calculation, toy numbers.
Okay, this framework is powerful. Let's try to put some numbers on it, even if they're illustrated toy numbers from the model. How does a potentially habitable rogue planet stack up against, say, an Earth-like planet orbiting a star?
Right. The sources provide comparative calculations using physically motivated, plausible parameters for each factor in the LPC and IPC equations. Let's look at a standard starbound Earth-like world first. This assumes it's in the habitable zone, so it gets a high score for stellar energy and reasonable scores for chemistry, stability, internal heat, and maybe moderate multiplicity if it has a moon like ours.
And the result for that baseline?
The model yields approximate probabilities. LPC, life probability coefficient, approx 9.7% semi and sen. IPC, intelligence probability coefficient, approx 7.8%.
Okay, so roughly a 1 in 10 chance for life and nearly as high for intelligence per suitable starbound planet. That's our benchmark.
Pretty much. Now let's contrast that with a rogue subsurface Earth think a type I world. Here, stellar energy is basically zero, but let's assume it has good chemistry and excellent long-term stability in its subsurface ocean. And crucially, let's give it high scores for internal energy, Minturn dollars, from decay and tides, and multiplicity, because it retained a large moon.
So it's banking everything on I and M. What are the numbers?
The numbers drop dramatically, as you'd expect, but they're crucially not zero. LPC per prox 1.5%, IPC per prox 0.48% day.
Wow. Okay, so the chance of life is down from nearly 10% to 1.5%, and the chance of intelligence plummets from almost 8% to less than 0.5%. That's a huge hit.
It is a huge hit per object. Let's look at one more. A rogue gas giant with retained moons, like a Type 2 system.
Huh.
Here, e$ 0. Let's assume high dollar knowledge from the giant's internal heat and its moon's tidal forces. Maybe knowledge and complexity are a bit lower because the potential life is atmospheric aerosols, perhaps a less rich environment than an ocean.
And the numbers for that scenario.
The model gives something like LPC approx BISN 10909 2%, IPC approx 0.50%.
Interesting. Still low, comparable to the subsurface Earth scenario. Slightly lower chance for basic life, maybe slightly higher for intelligence in this specific run, perhaps due to different assumptions about the complexity factor dollar.
All right, the exact numbers depend heavily on the input parameter assumptions, but the key qualitative takeaway is this. Yes, starbound worlds clearly have a significantly higher per object probability of hosting life and intelligence, mainly because that stellar energy term is such a dominant factor. It's just a massive energy fire hose, but rogue planets are absolutely not impossible candidates. If they can score highly on internal energy, and especially multiplicity, they can achieve a non-negligible chance for life, maybe in the 1-2% LPC range based on these examples.
And while that sounds low, the crucial you made earlier comes back now, doesn't it?
Exactly. The potential number of these rogue planets might be vastly larger than the number of nice starbound worlds. And that sheer quantity could change the entire galactic census. A small percentage of a huge number can still be a very large number.
Okay, we've established the physics makes life possible, if maybe less likely per planet. But let's run with that 0.5% chance for intelligence paying off somewhere. What would a society that actually beat those incredible odds look like? A civilization that evolved and maybe thrived entirely in the dark.
It's a fascinating thought experiment. Their entire existence, their technology, their culture, even maybe their psychology, would be shaped by constraints that are just totally alien to us.
Constraints born from never having seen a sunrise.
Precisely. A civilization on a rogue planet simply cannot afford the kind of wastefulness, the short-term thinking, or the reliance on easily accessible surface resources that star-powered civilizations like ours often take for granted. We're bathed in effectively limitless energy from the sun. They are not.
Their whole strategy has to be about surviving the long, permanent night. Indefinitely. Hashtag A. Survival priorities and goals.
So number one priority, absolutely non-negotiable, sustained energy. Without starlight, any long-term activity, heating habitats, growing food, running computers, circulating air, depends entirely on reliably tapping into those persistent, high-density local energy sources.
Geothermal, tidal, radiogenic decay.
Or maybe eventually engineered sources like fusion, if they can develop it using only the materials available on their worldlet. But they have to be able to access it, distribute it, and maintain the power systems basically forever. Failure means extinction.
Which dictates their architecture, right?
Yeah.
You mentioned thermal regulation.
It becomes paramount. They must minimize heat loss to the absolute physical limit. This means moving their entire population, their industry, their agriculture into incredibly well-insulated, thermally buffered spaces.
Deep underground, beneath the ice, inside engineered shells.
Likely all of the above, maybe habitats layered concentrically around the primary internal heat source, maximizing efficiency. They'd need materials with near perfect insulation, perhaps advanced metamaterials, vacuum gaps, maybe even exotic states of matter if they can engineer them, to stop precious heat leaking out into the void.
And resource management. I
Yeah.
would take it for granted that we can mine more stuff or find new resources. That's not an option for them, is it?
Not in the same way at all. This forces absolute resource circularity. They cannot afford any waste. Every atom of water, every molecule of carbon dioxide, every scrap of metal must be recovered, recycled, reused.
Near 100% material efficiency.
It would have to be the goal. Any leak, any unrecoverable waste product is a slow, inexorable depletion of their finite world. It would necessitate a total industrial ecology, think incredibly sophisticated, closed-loop life support, synthetic biology tailored to recycle everything with minimal energy input.
Which implies their long-term goals would be very different from expansionist starfaring empires, we imagine.
Probably much more conservative, much more focused inward. Their primary strategic goals would likely be maximize and stabilize their internal energy production, maybe even actively engineering tidal forces by subtly adjusting moon orbits over centuries.
And ensuring survival through redundancy.
Absolutely crucial for any truly long-lived civilization. They'd likely strive to establish multiple, geographically separated, independent biosphere vaults deep within their world, so that a single catastrophe, a technological failure, a disease, an internal geological event doesn't wipe them out completely. Redundancy is survival. Hashtag B, cultural and cognitive adaptation.
This kind of existence, needing millennia-long planning horizons, It must shape their culture profoundly. You mentioned risk-averse governance being compulsory.
It almost has to be. Short-term political thinking, factional squabbles that disrupt essential maintenance, those would be existential threats. Their institutions would need incredible stability, perhaps designed to preserve critical knowledge and technical skills across vast timescales. Maybe AI plays a role in managing critical systems impartially.
And who'd be the heroes in such a society? The politicians, the warriors.
Unlikely. The sources suggest a cultural shift where engineers and technicians are the elite. The people who understand, maintain, and repair the complex life support, the power systems, the recycling loops, they would be the most vital, the most revered members of society.
A culture where maintenance is maybe seen as a sacred duty.
It could well be. Reliability, meticulousness, interdisciplinary engineering knowledge would be the highest virtues. Craftsmanship elevated to an art form, because failure isn't an option.
And their technology would evolve down a completely different path from ours, wouldn't it?
Radically different. Consider just their senses. We are overwhelmingly visual creatures because we evolved under a bright star. They wouldn't be.
So a low light sensing culture.
Or perhaps a non-light sensing culture. They would likely develop incredibly sophisticated sensors for things that are more relevant in their dark environment. Think advanced sonar or seismic mapping of their internal world, hypersensitive infrared detectors, perhaps neutrino detectors to monitor their planet's core activity.
Maybe ways to sense gravitational fields or magnetic fields with high precision.
Exactly. Instruments to perceive the universe through fields and gradients and chemical traces, not primarily through photons. Their entire scientific understanding of reality might be structured differently.
And their engineering philosophy, not focused on speed or rapid innovation.
Probably the opposite, an emphasis on slow, durable engineering, building things to last for centuries or millennia. Systems designed for maximum reliability, robustness, and ease of repair, using only locally sourced materials. Planned obsolescence would be an unthinkable insanity.
You also mentioned intermittent biological activity. What does that mean? Hibernation.
It's a possibility driven by energy conservation. Since energy is likely the ultimate limiting resource, maybe large parts of their structure are run by extremely low energy autonomous robotics most of the time. Biological life, the citizens themselves might cluster in the most protected, energy-rich zones.
And maybe even enter states of torpor or suspended animation.
Perhaps. Entering low-energy metabolic states for long periods could be a survival strategy, especially during times when energy budgets are tight, or maybe during long interstellar journeys if they ever achieve the ability to move their world, consciously rationing their existence across the eons.
Wow, the psychology of that. A civilization rationing its very consciousness to survive. It's a chilling but fascinating image.
Okay, so we've painted a picture of how these rogue worlds might work, and how life, even intelligence, could theoretically adapt. This brings us back to the big question. How many are actually out there, and what are our chances of finding one, or maybe of one having found us?
Right. This is where the sheer numbers, the potential population size we discussed earlier, really come to play with that LPC-IPC framework.
Exactly. The sources perform some pretty stunning numerical modeling, taking the LPC and IPC probabilities we calculated and applying them to the estimated populations of star-bound versus rogue planets in the galaxy. And the results are, well, deeply counterintuitive for most people. Hashtag A, the population inversion, the census.
So how do they estimate the total counts? What assumptions go in?
They use what the sources call a medium rogue scenario. This isn't the most extreme estimate, but a fairly plausible one based on current thinking. It assumes that the number of rogue planets in the Milky Way is roughly equal to the number of planets bound to stars.
So null rogue equals null, about how many is that, roughly?
We're talking maybe 200 billion star-bound planets, so they assume around 200 billion rogue planets as well, wandering the galaxy.
200 billion. That's a lot of potential real estate,
Mhm.
even if the chance per planet is low. But hold on, how confident are we in that 200 billion number? That seems like the linchpin for this whole rogues might dominate argument.
That's a fair question. It is an estimate based primarily on two things. Dynamical simulations of planet formation and scattering, which show that planetary systems are very efficient at ejecting planets early on,
Okay, theory?
and more importantly, observations. Gravitational microlensing surveys like OGLE and MOA and upcoming ones with Roman Space Telescope consistently detect these short-duration events that are best explained by free-floating planets, particularly Jupiter-mass ones. The rate of detection suggests a very large underlying population.
So the observations support a huge number.
They point towards it, yes. While the exact number is still debated, it could be lower, it could be even higher. Maybe 2 or 3 times the number of bound planets, 200 billion, is considered a reasonable, perhaps even conservative, medium scenario based on current microlensing data interpretation. If the number is higher, the results we're about to see become even more pronounced.
Okay, understood. So, assuming that medium scenario of 200 billion rogues, they apply the average LPC and IPC scores we discussed earlier, factoring in things like the likelihood of moons, galactic habitable zone constraints, etc.
Right. And they calculate the total estimated number of worlds likely hosting intelligent life in the entire Milky Way.
And the grand total is?
Approximately 1.59 billion worlds with intelligence.
Okay, 1.6 billion intelligent civilizations potentially out there. That's a staggering number in itself. But how does it break down between starbound worlds and rogues? That's the crucial part.
This is where the inversion happens. When you break down that 1.59 billion total, planets in traditional starbound habitable zones, which have that high nearly 8% IPC per object, contribute about 0.54 billion intelligent worlds, roughly half a billion.
Still a huge number, but that leaves
the rogue planets, with their tiny IPC of around 0.5%, but applied to that enormous population of 200 billion worlds, they contribute approximately 1.04 billion intelligent worlds.
Wait, more than double the contribution from starbound planets?
In this plausible medium scenario, yes. Rogue planets could potentially host the majority of intelligent life in the galaxy.
That really is the aha moment, isn't it? The core takeaway. Even though the chance per planet is much lower for rogues, their sheer population size completely flips the script. It compensates for the low probability.
It's a galactic numbers game. Quantity has a quality all its own, as they say. The sheer volume of these dark worlds could make them the dominant havens for life and intelligence, statistically speaking. #tag B solar system encounters.
Okay, so the galaxy might be teeming with potentially 1 billion intelligent rogue civilizations drifting through the dark. That raises another question. What's the chance that one of these wanderers has ever passed close to us? Through our solar system.
A fascinating question. The sources calculate this probability based on the typical relative velocities of stars and rogue objects in the galactic disk, around 30 kilometers per second or so.
And what do the numbers show for close passes?
Over the sun's entire 4.56 billion year history, it's likely experienced about 5 passages of a rogue planet within about 1,000 astronomical units.
Oh, 1,000 AU. That's way out there, past Neptune, in the realm of the Oort cloud, right?
Exactly. It's far, but close enough dynamically to potentially perturb the orbits of those distant comets in the Oort cloud, maybe sending some of them tumbling into the inner solar system. Some comet showers throughout Earth's history might have been triggered by these passing rogues.
So encounters at that distance seem plausible, maybe even expected. What about closer encounters?
Yeah.
Like inside the planetary region?
If we tighten the encounter distance significantly, say to within 100 AU, that's only about 3 times Neptune's distance, close enough to potentially disrupt the orbits of the outer planets, the probability dropped quite a bit.
How low?
The chance of such a close encounter happening while the sun is in its current relatively sparse region of the galaxy is estimated at around 5% over the full 4.56 billion years. So it's low, but it's not zero. It could have happened.
But there's a caveat there, isn't there? About
Yeah.
the sun's birth.
A crucial caveat, yes. Encounters were likely much more frequent very early on, when the sun was still embedded within its dense, chaotic birth cluster of stars. Most of the dynamical sculpting of the outer solar system, like the formation of the Oort cloud itself, probably happened back then due to interactions within that cluster, including passes by other stars and perhaps many more rogue planets.
Okay, so maybe 5% chance of a close pass by any rogue in the current era. Now let's fold in the intelligence calculation. What's the chance the sun has had a close encounter? Let's use the 1,000 AU radius again with a rogue planet that was actually hosting an intelligent civilization.
Right. Combining the dynamics with that potentially large population of intelligent rogues, 1.04 billion, the calculation suggests the chance of our sun having passed within 1,000 AU of an intelligent rogue civilization at some point in its history is around 3.6%.
3 or 4%. Again, low, but definitely not zero. It's actually conceivable that an alien intelligence on a dark world drifted right through the outskirts of our solar system sometime in the last few billion years.
It's conceivable, yes. But there's another big assumption baked into that number. It assumes that these intelligent rogue civilizations are very long-lived, surviving for billions of years to build up that large, steady population. If intelligence on rogues tends to die out quickly, then the probability of encountering one drops significantly.
So the conclusion is that physical contact, or even a close pass, is extremely rare.
Vanishingly rare, most likely. But remote detection might be another story. If they exist in large numbers, maybe we can find evidence of them without needing them to bump into us. Hashtag C, observational signatures, how we search.
Okay, so if direct encounters are out, how do we actually look for these things? Especially the potentially active or even inhabited ones. They don't have a star making them shine. What signatures could they produce?
That's the billion-dollar question for observational astronomy. We need to look for subtle signs that betray their presence, either natural signs of activity or maybe even artificial ones.
Let's start with the main tool we have now, microlensing.
Right. Microlensing events are still our primary tool for just counting them, for getting a census. As we said, a rogue passes in front of a distant star. Its gravity bends the starlight, causing a temporary, characteristic brightening of the background star.
And short events mean small, planetary mass lenses.
Exactly. Events lasting only hours or days strongly indicate a planet mass object that isn't bound to the foreground star it seems near. So microlensing confirms the population is large, but it tells us almost nothing about the individual rogue planet itself. Is it hot? Cold? Does it have moons?
So to learn about habitability, we need other methods, like looking for their heat.
Yes, the most direct way to probe for activity is looking for thermal or mid-infrared excess. Even a rogue planet isn't at absolute zero. It has some residual heat from formation or ongoing radiogenic decay, or especially that tidal heating from moons.
So it should glow faintly in the infrared.
It should have a faint thermal glow, mostly in the mid-infrared wavelengths, maybe around 5 to 100 micrometers. The challenge is detecting that incredibly faint heat signature against the cold background of space, especially with no nearby star to provide contrast.
Like finding a needle in a haystack, a slightly warm needle.
It's incredibly difficult. We're pushing the absolute limits of sensitivity with space telescopes like the Spitzer Space Telescope in its later cold phase, and now, crucially, the James Webb Space Telescope, JWST. Objects like WISE 0855 are prime examples, extremely cold, faint objects detected directly in the infrared with no associated star. They could be the prototypes for the massive rogue population.
Okay, heat is one signature. What about magnetic fields? You mentioned type 3 cryogenic giants might have strong fields.
That leads to another potential signature, auroral radio emission. Just like Jupiter, with its strong magnetic field and internal energy source, interacts with particles to produce powerful polarized radio bursts.
A massive magnetized rogue planet could do the same.
Potentially, yes. If it has a strong internal dynamo generating a magnetic field, and maybe it's sweeping up sparse interstellar plasma, it could generate detectable low-frequency radio waves. Seeing that characteristic auroral radio signature coming from a point source with no associated star would be a smoking gun for an active, magnetized rogue.
So radio telescopes like LOFAR or the future SKA could potentially pick these up.
They're ideally suited for searching for these low-frequency signals. It's a key observational avenue.
And you mentioned a relatively new finding in the source's evidence for disks around some of these objects.
Yes, this is really exciting and very recent. Some studies looking at infrared excesses around known free-floating planetary mass objects are finding evidence consistent with warm circumplanetary disks of dust and maybe ice surrounding them.
Disks around rogues, what does that imply?
It's huge for habitability. It strongly suggests ongoing dynamical processes. These disks could be the sites of moon formation, or they could be leftover material from moon formation or collisions. Either way, the presence of a disk significantly boosts the odds that the rogue planet has moons.
And moons mean tidal heating, boosting that critical M factor.
Exactly. Finding rogues with disks preferentially targets the systems most likely to have significant internal heating and thus higher habitability potential according to our model. It's a crucial link.
Okay, those are natural signatures. What about looking for artificial signs, techno-signatures?
That's the ultimate long shot, but you look for anomalies that are hard to explain naturally. Things like narrowband radio signals or laser pulses that seem directed or structured.
SETI, but aimed at dark spots instead of stars.
Essentially. Or perhaps more plausibly, looking for thermal anomalies. Instead of a uniform faint glow, maybe you detect a localized, unusually warm spot on a rogue planet in the mid-infrared.
Waste heat from a Type V civilization's power source.
That would be the interpretation. A concentrated mid-IR excess, inconsistent with natural global cooling, could potentially be the waste heat signature of large-scale artificial energy generation. Finding that would be monumental.
So practically speaking, what's the recommended search strategy going forward?
It needs to be multi-pronged and highly targeted. Use JWST's incredible sensitivity for deep infrared spectroscopy on the coldest, most promising rogue candidates identified by WISE and Spitzer. Look for thermal gradients across their surfaces, or search for atmospheric absorption lines indicating unusual non-equilibrium chemistry that might hint at life or activity.
And combine that with other methods.
Crucially, yes. Cross-match the targets from microlensing surveys with deep radio surveys from LOFAR, VLA, Meerkat, and eventually the SKA. We want to find those objects that show signs of being active rogues, ones that exhibit both an infrared excess, suggesting internal heat, and potential magnetic activity, radio emission, or evidence of circumplanetary material. Those are the prime targets for follow-up. Hashtag Shag Outro.
So wrapping this all up, what does this deep dive really tell us?
I think the main point is that rogue planets shouldn't be dismissed as just frozen, dead chunks of rock drifting aimlessly.
They're potentially incredibly diverse worlds, active environments.
Exactly. Where life, powered entirely by internal forces, heat from within, tidal forces from moons, might genuinely find a way to thrive, even in perpetual darkness. And the latest observational data, especially the microlensing census and the hints of circumplanetary disks, seems to support the idea that a large population of these potentially active worlds really exists.
And some of them might have the exact conditions. High internal energy and complex systems with moons that our habitability model says are the most promising for life in the dark.
Precisely. So the key takeaways for me are, first, life in the darkness is physically plausible, but it relies critically on those internal energy sources and the complexity multiplier that comes from having companions.
Second takeaway. The sheer number of rogue planets estimated to be out there means they could, counterintuitively, end up hosting the majority of the Milky Way's life and even intelligence just by overwhelming the higher per-planet odds of starbound worlds.
Yeah.
That population inversion is maybe the biggest single revelation here.
Agreed. And third, our search strategy has to get smarter. We need to move beyond just counting them and focus on identifying the active rogues, the ones showing multiple signatures like infrared excess, magnetic activity, or disks, because those are the needles in the haystack most likely to harbor something interesting.
It really reframes the search for life, doesn't it? Looking in the cold, dark places, not just the warm, sunny ones.
It forces us to be more creative, certainly. And thinking about those hypothetical type V civilizations, or even just long-lived natural biospheres on rogues, their entire existence hinges on extreme long-term planning, absolute risk aversion, and that perfect circular economy we discussed.
If they can manage that incredible balancing act for geological ages, they could potentially outlive stars like our own sun.
They could become incredibly ancient. Which leads to a final provocative thought to leave our listeners with.
Go on.
Consider this. If an intelligent civilization is out there, quietly migrating through the interstellar darkness on its own self-contained planet ship, are they just a relic of a star system that died long ago? Or are they perhaps demonstrating the ultimate endgame for survival? A blueprint for how life might persist across cosmic timescales long after stars fade? Are we looking at the past or a potential future?
That is definitely something to mull over. Thank you for this fascinating journey into the dark, and thank you all for joining us on the Deep Dive.